I cringe whenever I see something like this. It wrongly suggests a direct link between bank angle and stall speed, which is simply not true. Worse, it distracts from the one and only thing that can stall an airplane. This association between bank angle and stall speed should be removed from pilot training entirely. Instead, the only thing we should mentally associate with a stall is the position of... Actually, no. Let's do a quick quiz and see who gets it right. The only control surface that has the ability to directly stall an airplane is the A. ailerons, B. flaps, C. elevator, or D. rudder. Only one of these is correct. Take a moment to think about it and I'll confirm the answer shortly. To be honest, I do know why it's thought that increasing bank angle raises stall speed. In an indirect way, under certain conditions, it's true. But saying that increasing bank angle increases stall speed is fundamentally misleading. To understand why bank angle is irrelevant to stall speed, let's quickly revisit what causes a wing to stall. A wing stalls when it exceeds its critical angle of attack. That's the angle between the oncoming airflow and the wing's chord line. For most light aircraft, that's around 15 degrees, but varies slightly with different airfoils. As angle of attack increases from 0, lift also increases, but once past the critical point, lift drops off sharply. We control angle of attack with the elevator by using the yoke or stick. Pull back and angle of attack increases. Push forward and it decreases. That's all there is to it. When an aircraft banks, its angle of attack doesn't automatically change. The wings still meet the oncoming air at the same angle. However, as it banks, the lift vector tilts away from vertical. Lift acts perpendicular to the relative airflow. So, as bank angle increases, less of that lift acts vertically to oppose gravity. The steeper the bank, the more the vertical component of lift decreases, causing the aircraft to descend. To maintain altitude during a bank, the pilot must increase total lift. That means increasing the angle of attack by pulling back on the yoke or stick. This is why it is taught that bank angle increases stall speed, even though bank angle itself has zero effect on stall speed. It is only when it's required to maintain altitude that bank angle will increase stall speed, which is due to increased load on the wing. You might ask, but isn't maintaining altitude the norm when turning an airplane? And that's a fair question, as it is the norm to control vertical speed while turning. But let's look at where inadvertent stalls usually occur, which is often in and around the circuit. Now think about the typical turns in a circuit. The upwind to crosswind and crosswind to downwind turns are usually climbing turns. Downwind to base and base to final are descending turns. There could be level turns in a circuit, but most aren't. In a descending turn at a given airspeed, the bank angle required to stall will be higher than for a climbing turn, because in a climb, more up elevator is used even before starting the bank, and it will stall at a lower bank angle. That is the problem with this kind of bank angle versus stall speed diagram, which is often shown in textbooks or briefings. They rarely clarify that it only applies to level flight. Without that context, they are misleading and promote fear of banking an aircraft without offering any explanation as to why we should be careful with high angles of bank. The truth is, an airplane can be in a 60-degree bank and still fly safely below this published stall speed for that bank angle. It's not the bank angle that stalls the wing, it's the elevator input. If maintaining altitude is not a requirement and you keep the stick neutral, it can't stall. With the yoke anywhere between pushed fully forwards to about 80% of the way pulled back, the wing can't stall regardless of bank angle. 80% backwards is not the down to the millimeter precise yoke position where the wing will stall on all light aircraft. Some will stall only when pulled fully back, while others may stall at slightly less than 80% pulled back, but this should give you a rough idea. This holds true at all airspeeds, whether approaching to land wings level or in a high-speed turn. Next time you go out for stall recovery practice, bring along a proficient rated pilot or flight instructor. Let the instructor perform some stalls while you closely watch the yoke or stick. You'll notice that the stall only occurs when the control is pulled fully aft or very close to it every single time. Interesting, isn't it? Now try a stall yourself. Set up for a stall as usual, but instead of pulling the yoke all the way back, stop at about 75% backwards travel. Don't pull back any more than that. Now try to make the plane stall. It won't. It can't because you deliberately kept the angle of attack below critical with the yoke. The plane may descend rapidly, but the wing won't stall. This principle applies to all airspeeds, bank angles and attitudes. A stall only occurs when the wing exceeds critical angle of attack, and that can only happen with the stick pulled nearly fully back. Keep in mind, doing a power-on stall can make the plane stall with slightly less up elevator, as the prop wash blowing over the tail gives the elevator additional pitch authority. But the fundamentals remain the same. That stick needs to come most of the way backwards to stall the wing. So, back to the quiz. The correct answer, of course, was C, the elevator. Now, digressing a bit, some might argue that you can also stall the plane with rudder or ailerons by inducing uncoordinated flight. After all, we're taught, with good reason, to always remain coordinated to avoid stalling. But uncoordinated flight doesn't affect angle of attack. Instead, uncoordinated flight reduces overall lift, which causes a descent. To counter that descent, the pilot needs to apply more back pressure on the controls, just like trying to maintain altitude in a turn. And as we've already said, that increases angle of attack. Increase it enough and the wing stalls. Still not convinced? Consider a full rudder forward slip on final approach. It's as uncoordinated as it can get. Yet it doesn't stall the airplane. Why is that? Because you're not pulling the yoke back anywhere near fully aft. In fact, you're likely pushing slightly forward to keep airspeed on target due to the increased drag. That's what increases your descent rate and is why you are slipping in the first place, to descend faster without increasing airspeed. Due to that forward input on the yoke, the wings remain well below critical angle of attack, even though it's uncoordinated flight. What about a skidding turn? Pushing too much rudder causes a skid, and we know how dangerous that can be, especially in the circuit. So, can the rudder stall an airplane? Indirectly, yes, but just like bank angle, it requires an increase in angle of attack. It's not that a skidding turn is inherently more prone to stalling than a slipping turn. The real danger is that a skid can easily result in an instant spin, and inadvertent spins in the circuit are almost always fatal, and that's why skidding turns should be avoided entirely. In a skid, the inside wing experiences a higher angle of attack and is the first to stall. When that happens, the aircraft can snap roll inverted into a spin, a classic and deadly base to final accident scenario. So yes, a skidding turn can result in a stall at higher speed than wings level flight, but again, only if up elevator is applied to increase angle of attack sufficiently. With the elevator forwards of say 75% backwards travel, even a skidding turn won't result in a stall, because you're not commanding a high angle of attack and the angle of attack of that inner wing remains below critical. This is not something to go experiment with. That is not what I'm saying. Always stay coordinated during turns in the circuit. But the key takeaway here is that it's the elevator, not the ailerons or rudder, that stalls a wing. So, to avoid inadvertent stalls, don't focus primarily on bank angle. Instead, pay close attention to how far you're pulling back on the yoke or stick. Practice stalls frequently, at a safe altitude of course, until it becomes muscle memory that when the stick gets here, you're about to stall regardless of airspeed or bank angle. An angle of attack indicator would serve the same purpose, warning you as you near critical angle of attack. But most airplanes don't have one. Fortunately, you can treat the fore and aft travel of your yoke or stick as a kind of poor man's angle of attack indicator. Think of it this way. With the yoke or stick between full forward to just past halfway back is a green angle of attack indication. From there to about 75% back is a yellow indication. And the final 25% is a red indication. There you go, now you've got a crude angle of attack indicator in your airplane. So let's sum up the entire video in one sentence. This does not stall aircraft. This stalls aircraft. Thanks for watching. See you in the next one.